All right, it looks like we're going. It has been quite some time, but we are going, and it is good to see everyone here. Looks like we got good levels here. Yeah, kind of a last minute stream, but yeah, it's good to see everyone, and yeah, I'm here. Welcome to the stream. My name is Jason Watts. This is the channel for all of your Siemens motion control needs. Hopefully you are having a good Valentine's Day. This is Valentine's Day 2025. It has been quite some time. I think this is actually my first stream that I've done in 2025. So welcome to 2025 for all of you that are here. I kind of got stuck in the office. I was going back and forth between doing this stream today or tomorrow, but we do it today just because traffic is terrible here in Atlanta, where I'm located in one of our lab slash shops. And so my name is Jason Watts. I am the CEO founder of a little automation company out of Alabama called Alpha Industrial Technologies, and we do all sorts of different stuff. Some of it is based around motion control. We do some winders, some OEM equipment design from that, but we have been doing a lot of agriculture stuff. So we are based out of Alabama, but I am here in Atlanta, Georgia. I'm in our lab in West Midtown, just to the west of Georgia Tech. And like I said, traffic was pretty bad, so I just decided to go ahead and do one of these streams. So don't know if I'll have anybody really coming in live on the stream, but if we do, welcome. And if you do drop in live while you're here, be sure to drop in that you're here. Say hey. As always, I'm just getting logged in here on my phone just in case someone is actually as in, and so yeah, we'll be going from here. So hopefully you've had a good week, and it's Good Friday, and like I said, it's Valentine's Day. But today we're going to be talking about some pretty cool stuff, some very nerdy stuff, and I'll try to keep it pretty quick because it can get really deep, and this isn't going to be like a deep in what's it called, the deep into the weeds of this Fourier transform and frequency domain analysis. But if you want to know more about what's going on, I'm going to give you just a little bit of an overview, and we're going to have at the very beginning of this session a little bit of about what is frequency domain analysis. What does it actually mean, connecting it to the real world? You may have heard that in some classes at university, but we will be going through a little bit of that, and then trying to determine or trying to show you how you can actually use a Siemens S120 and some of the other stuff. Some of the other Dynamics offerings have them as well. But there's actually a pretty, I don't know, it wasn't very well known when I was an application engineer for Wesco, that you actually could do FFTs, so fast Fourier transforms, inside of Starter. And so we're going to go through how to do that, do this frequency domain analysis on some of your traces, and then how to put in some filters to kind of do a little black magic on your drive systems that may be giving you a little trouble. I'll say we got a couple of people in the chat coming in asking about some SCADA development for Alpha. Alpha absolutely does SCADA development, by the way. We have done the Siemens-based stuff, but we prefer a SCADA platform called Ignition. One of the other owners, Brandon Hughes, he is a wizard at Ignition, and so I let him do that because that is his expertise. We do a lot of drives, or at least I do. And so without further ado, I want to kind of get going into this next little, let's see, the next little session here. So that is starter. This is paint. And I brought up paint because I wanted to kind of go through it first, kind of talking about what is this frequency domain analysis. And again, like I said before, you may have experienced some of this in maybe a controls classroom, a class at university, and we're not going to get too deep into it because this is kind of more of the practical side of it. I was talking to someone kind of on, I think it was on LinkedIn, that I personally struggled with the class controls, even though at the time that I was taking it, I had 8 or 9 years of actually working with controls in industry. Industrial controls and designing control systems are kind of two different things. But one of the things when you're designing control systems, that you have to work with these mechanical systems, and you'll hear these words called, or like resonance and kind of gains and all of these different things of your control loops that end up interacting in ways that cause issues. And if you have taken one of these classes, you have done probably one of two things. You've either done what's called a Laplace transform or a frequency transform, so a Fourier transform. And what we will be doing is talking about the FFT, so the fast Fourier transforms. Welcome to the stream, everybody that's coming in. We're talking about some major nerd stuff. And so what does this frequency domain, the just base topic, what does it actually really talk about? And so what this is the basic concept of frequency domain analysis is that any mechanical system cannot react instantly. And that may sound like, okay, we're talking about frequencies like radios and cell phones and things like that, right? Well, that's part of it, yes. That's electrical frequencies. But every mechanical system will have things called resonance in them. In that example of just talking about like a radio, an FM radio, like a dipole antenna has resonant frequencies. And so the electrical resonance will give you, I guess, your best gain on your antenna if you are adhering to certain properties of that antenna. On like a CB radio, if you've ever messed around with those, the what's it called? It's some ratio. I can't remember the name of the ratio. If you know in chat what the ratio of the length of the antenna is that you have to have on a CB radio based on your induction of your actual radio, you actually are physically cutting the antenna on a CB radio in order to actually make it go out. So, and that's this resonance property. So one thing that we talk about a lot in control systems is we want to change, say, the speed of a system. So let's take a moment to just kind of look at, and that's not showing up there. So let me actually get this working correctly because I realized something. Let's do this now. So we're going to draw a graph, and that is actually showing up this time. So we're going to draw a graph here, and on this graph we have say the RPM of a motor. So this is the speed of this motor, and this is going to be in time, and this is kind of what we're used to actually experiencing in what is called the time domain. So this is the time domain, because we're talking about time. Everything's in reference to time. And so as we go along, we may want to take some, say this is 100 RPM, and we want to bump up to, say, 500 RPM. right? So that's what we would actually want our control system to do. And we would send it a signal and say, all right, we want to jump up at some pace like that. And so we want it to go up to 500 RPM. Well, this may be our signal, our set point signal. What I was talking about before is a physical system cannot react this way. There is no way that this physical system can instantly go from 100 RPM to 500 RPM. It could go very quickly, but not instantly. Instantly is what we've attempted to draw here. And so what will actually happen is we will get some sort of lag and then overshoot and then some sort of settling like that. It'll look something like that. Well, in every mechanical system, in every physical system that is subject to the laws of physics, it will look something like this. And so even if you're just, say for example, a tuning fork or piano key, if you take and attach a string between 2 points, you will get what are called resonances. And so harmonics, you may have heard those as well. And so what you can see is you can have different orders of harmonics. So a string will vibrate at a certain frequency based on the tension. And that is because the tension will have some something like this, and you will have multiple frequencies that resonate on this string. And so just a kind of a way to think about the resonant properties of a mechanical system is they will sometimes literally make sound, but if you try to vibrate a string on a piano at a different frequency other than its resonance, it will become damped. And so it will dampen itself and it won't ring out. It won't vibrate. It will just die. And that is the mechanical properties of the tension of that string. So let's take and kind of delete this out and go back in here. And so one of the things that we learn is that every mechanical system is actually not just made up of one frequency, but really actually an infinite number of frequencies. Now, just like we could pluck that piano string and it won't make a noise except at that resonant frequency, all the other frequencies aren't out. They're still there. That motion can still be composed of multiple frequencies. Now, here's the thing, it's called the superposition principle. And again, we're not really going to go into very much. And so what we will look at is in the time domain, if you take a signal and start adding in higher and higher frequencies or harmonics of the same frequency, you can actually create this step function, which we created here in black. This is the step function. You can actually kind of simulate that as saying, okay, we're going to take an infinite number of frequencies, because we see this has some sort of frequency here. That has some sort of periodic motion, some sort of kind of like a sine wave. Well, let's increase that frequency and start kind of adding in different frequencies, and you can kind of get a motion that looks, if you add everything together, then it will create a step function. So this is in the time domain, and so it kind of looks a little weird in the time domain. And so in control theory and in signals and systems particularly, this Fourier transform says, okay, we can take any signal, any function, and break it into its frequency components. Just like each one of these red lines over here creates, is a different frequency. And we add them all together, and we can create any function if we use enough frequency or enough individual frequencies. Well, it doesn't really look really interesting in the time domain. It looks kind of weird. So when you transform into the frequency domain, your graph of a signal looks very different. So let's take an example really quick of a perfect sine wave. We try to do a step function because that's what we're kind of familiar with just in the control world. And so let's take it to the math world for a second. And let's just take and select all of this. Let's just do this actually. And delete. And go back in. And let's just draw in the time domain a sine wave. We kind of know that if this is 0, 1, -1, it will look something like this, right? And so that would be 2 pi, right? That's pretty familiar to you, most likely. Well, you can see this is an oscillating signal in the time domain. Everyone's kind of familiar with that. So let's go through and change this into the frequency domain. So let's change this to, instead of time, let's make this frequency. And the way that you would have this is that sine wave has some sort of period. It's a period of what, omega pi or whatever it is. It has some sort of frequency to it. In electronics in the US or in power systems, that frequency would be based off of 60 hertz. Elsewhere in the world, you're going to be looking at 50 hertz. And so a pure sine wave AC power voltage in the US would be 60 hertz. And if you were to do an FFT, or just a Fourier transform on a pure sine wave, it would look something like this. It would be, that is, there, 1. So it would just be a single arrow. And this, if you were doing a voltage waveform and you did on power, then hopefully if you had an absolutely pure sine wave, you would get all of your, at 60 hertz in the US or 50 hertz for everybody else that's watching this. And it would just be a line, and it would just be a point. And because the entirety of that signal, that pure sine wave, resonates at 60 hertz. Now, if you had some harmonics in it, say you had a little bit of distortion, you might start to see maybe at 120 hertz, maybe there's something there. And maybe further out at 240 hertz, you also have a little component. Hopefully, these out here would be much, much smaller than your 60 hertz. Because otherwise, you're going to have a lot of harmonics. And so that's how this frequency domain works. It breaks everything down into its frequency components. Now, if you've come here and say, Jason, I know all of this. I've been to school. We did this. I totally understand all of those systems. Well, how do you use that in a mechanical system? And that's what we're going to talk about. So if you can identify a mechanical resonance. So think about it. If you are trying to be at steady state, if you are trying to run at that 500 RPM, you would want all of your frequencies to be very close to zero. You would want it to be very, very close to zero. You would want very little oscillation, because the more oscillation means that the more you're going to get stuff in this area here. And we're going to look at that sort of stuff here in a second. But remember, a DC, a direct current, or a non-oscillating, so a perfectly stable control signal, is going to have a resonant frequency of 0 hertz, because it doesn't oscillate at all. Well, we know that no matter what, there's going to be a little bit of oscillation in a control system. And most of the time, it is based on the fact that you have something that you're not quite compensating for that's mechanically out there. Let's talk real quick about mechanical systems that might give you a little problem. So the easiest to think about and the easiest to kind of work with is if you have some sort of spring involved, some sort of tension. You know, we talked about that piano string, that guitar string earlier. Well, what if we actually had a conveyor belt kind of like this, and we had a tensioning device here that we could tension and put a force out. And so essentially what we would be doing is changing the force on this belt. That would be the same way as taking that guitar string and making it tighter. So if we moved this out, it would make that belt tighter. Now, a Kevlar reinforced rubber belt may not have a lot of vibration in it, but that little bit of vibration could show up in your mechanical system and cause some issues. And we're going to talk about how to see those issues in starter here in just a second. So the most easy ones that this sort of analysis will be able to kind of tune out will be systems that have some sort of spring constant. So if you have 2 points and you're kind of pulling like a webbing, or you have some sort of gear, so anything that you're having to keep some sort of tension on, a web, a sheet, a chain, something like that, is going to have some sort of spring constant. Now, it may be very low, but it could be very high. Some of the most complicated pieces of equipment are high-speed winders, because you start getting into these higher frequencies and your machine starts vibrating, and it starts exciting this mechanical resonant frequency of your equipment. It doesn't have to be a spring. It can be a piece of metal. It can be a fixed structure, but you could be vibrating it in a way that excites some sort of mechanical resonance. And you'll be able to see it with this here. So the easiest to see, just know, is in the spring constant. And where you will see this effect will actually be in the current or torque of your motor, because ultimately your motor torque is what is actually interacting with that mechanical system. It is the thing that is making the mechanical system move. And so if you see ripple in your torque, then it could be because of some mechanical resonance in your system. So let's flip over to starter, and I'm sure all of the Siemens people in here will be sitting here saying, "Wait a second, Jason, you said that will be, sorry, you said that starter is kind of an obsolete package, that start drive is your package that you really want to use now. Well, starter has this easy FFT functionality built into it, whereas I'm not aware that start drive, at least the versions that I use of start drive, have this functionality. If you're watching this and you say, hey, yeah, it does in version 18, 19, 20, let me know in the comments, because that definitely is something that would be a powerful tool. And yeah, so I'm going through and having to swap over a little bit on this, because I want to be able to commentate on what we have actually going on here with this, or annotate, I should say, not commentate. I commentate all the time. But what we have here, I just saw a text message from my wife, so I need to make sure doing a quick read. So one of the reasons that I brought this up was, or this system up, is that, let me put, I think I need to go here. Yep, so my head's here. All right, so in order for, so one of our members, which by the way, if you don't know, we do have memberships, and I will actually be providing these files to the members in the member archive for those that are at different levels. I also have a document that I built that went through this process, and I'll put it in both levels of the membership, because one of the members was kind of talking to me about a linear motor that possibly has an issue with some of this analysis, and this was what brought this up. And well, I said, okay, I know we can do this in starter. You've got an S120, they've got a current set point filter that we can use to do this. So what I want to do is show you how to get an FFT diagram out of a motor trace. So if you're not familiar with starter, it is a very powerful tool that's been out for a very long time, and it is free. It is a free download and works with all Dynamics drives. You don't have to be integrated into the PLC software. You can go download and work with the drives directly without having to use TIA Portal. Start drive inside of TIA Portal is amazing. It's awesome, but it has, because it's involved in these bigger systems, it doesn't have quite the exact drive specific stuff that we'll be talking about, which it's okay. Let's go. And first thing we want to do is, on this project, this is a little S120 test project. And if you didn't know, even if you are in a project that is not online, you can go through and pull up measurements, traces. And so what I have done is actually pulled up some traces from another project, from one of my customer projects that I was just doing a little bit of tuning, and I had pulled up this in here in order to actually check out some of these frequency domain type stuff on it. And so what we have here is we have our measurements. If you I'll show you real quick how to set up a trace, because we are wanting to trace the torque, the actual torque value from our system during runtime. Now, you may want to do this at a couple of different frequencies, a couple of different speeds, speed up, slow down, but you want it to be at steady state, because for the most part, mechanical resonances will show up either in a certain frequency band, and they'll start to vibrate. You'll start hearing these noises, and you'll see this current or torque ripple inside of the torque inside of frequency band, or you will kind of see them at basically every stage. So just go through, and if you're not familiar with the trace function, you can bring up the trace up here at the top, say device trace. you are going to select R78, that is the current actual value, or you can use R80 torque actual value. Pretty much the same thing. Torque is going to be, again, the thing that actually makes it work. Current, there's a little bit of math involved in order to get current to torque, but we are using a current set point filter, but torque and current are going to be in the same, they're going to resonate in the same way. So you'll see, hey, Jason, you said you need to be working with R78. In these traces, it's R80 because it is a torque. Sorry, but the case will be in point. So I've got some measurements here of previously saved traces, and I've just brought them up. And once you take these traces, like for example, if I were to do this endless trace, I would just click my little play button, or sorry, I would save, download the trace, and then I would click the play button, let it run for a little while, and then click the stop button, and it would record a measurement. You do that a couple of times, and your measurements tab will start to look like this. Or you can do like I did, is save some measurements from a previous time, click open, and find that trace file, and then import it in. I've done that on 2 different traces. You can see I've got this accumulator tuning and then a traces.trc. So I'm going to add a FFT to this bottom trace. First thing we'll do is we will select the measurement that we are wanting to trace or to add. Then we're going to go over here to the function button, the mathematical processing, and all we have to do is select frequency range, and then we can select the signal. And then in this one, we only have one. We have that R80 that I talked about before. And so we click it, and I click accept. And now you can see up here that there is now a mathematical processing of an FFT on signal 1. Now, if you notice down here, you can also do Bode diagrams, the transfer functions, all of those. You can absolutely do those. We're not going to get into those. There is a Bode diagram on here, so if you know how to kind of interpret those, we may do one about that. But the easiest thing here is to get into this frequency domain. So we've got that. We say OK. You can see it churns. It creates this FFT. And now that time domain is something that you may be used to. Okay, you can see I sped it up from 0. It went up to the torque went up to 170 Newton meters, kind of leveled out at 170 Newton meters for a little while, and then dropped down a little below 0, and then kind of sitting there around 0. So let's take and look at what that FFT diagram looks like. And it should be anticlimactic. But here's the thing, you know, when we were talking about the little, the perfect sine wave in this little section, let's take and look and see. We can see, like in this little section here, we have kind of this little sine wave here, you know? Let's go. So we can see that there is this little sine, and it's not quite perfect, but it's definitely oscillating. And you can also see up here, you can see there's a pretty definite signal that looks like that on this. So we can see that there are some frequency domain components in this. There are some oscillations. So let's clear that. Actually, let's do that, and then go back to this. So we would expect to see some spikes at something other than 0. And you can see that, yeah, we do have a lot of spikes down here in this range. Most of the stuff is down below this 20 range. We can see something here. We can see a little something here. But for the most part, it very much goes like that. Meaning there's a lot of stuff down here Not a lot up here. So let's clear that. And now I want to show you, let's zoom in, because there is some potential issues with this, because we know that we saw that oscillation. So let's zoom in down here at, undo zoom completely. And so what I want to do is I want to zoom in down here, because this kind of shows you a little bit of what I'm talking about with these peaks, because we do have a couple of spikes that are outliers, right? And if we look at that, that looks like about, we'll say 33 hertz. Okay, and this spike is pretty pronounced, and it is at, we'll say 16. Actually, it is 17 hertz. Okay, so, and what that does, and what is that is doing, is it is taking and looking at that trace and breaking down any of those frequency components. Obviously, you can see most of this stuff is very high, down very close to 0, 2.5 hertz, like in that sort of range. So, but these little spikes come up, and the thing about it is they are above 1. So they are contributing to a little bit to this. Now, I will say this value over here, what that value has to be before it starts resonating depends on the system. If you have a really tight or a really tight system, then that might be something in the range of like a 0.9 or 0.8, something like that. But normally, if that is over 1, there is ringing going on in that. So let's take, and for example, what we want to do is we would love to take and put in some sort of filter to be able to say, hey, take that component, that whatever that is right there, we want to just kind of take and smash it out. We want to stop that from affecting our system. We want to take that band and stop it. I intentionally use that obviously if you're used to filtering out current waveforms and things like that, you know we're about to put in a bandstop filter. And so in a perfect world, we would want to counter, see how this kind of is down near 0, goes up, and then comes down like that. In a perfect world, we would want to make a bandstop, a filter that takes and says, okay, inside of this area here, I want you to completely ignore that. I want you to quash that. I want you to squish it. And I want you to take it all the way back down to the level down here with everybody else. And yeah, we could probably do that same thing here, but it's down at a very low frequency. So let's just make, for this value here, we're going to call it 33 hertz is where this spike is. We're just going to call it that. And so let's make a bandstop filter that covers this range here. And so we want to cover at least from 31 to 35 hertz. We want a bandstop filter for that band, that range of values. So that's what we're shooting for. And so what we will do is in your drive, now again, this is just a random drive. I pulled up these traces, but say that I actually trace this on this drive number 1. I would come down into open closed loop control and then go to current set point filter and double click. And you have two set point filters here that go into the into your current controller. One is already enabled, as you can see, it's effective. Well, we want to use this second one and add in a bandstop filter. So what we have here is what is automatically engaged, and this is by default, is a low pass. And this is just trying to filter out all of the noise because this is a 2 kilohertz system. We want to try to filter out anything effective that's coming from just the control system itself, noise in the control system. Well, here, what we want to do is select band stop, and then we want the notch frequency to be, what was that? We said 33 hertz, right? 33.0 hertz, right there. And so remember, we wanted our filter, our bandwidth to be between, we wanted it to be between 31 and 35 hertz. So let's just say that that is a 10 hertz bandwidth. Now that is pretty tight. And now the notch depth is endless. So it will, at that point, it is actually going way down. And if we expand this out, you can see that it actually is at that notch, it is all the way down. So a wider bandwidth gives you more capture range on that. So remember, we had a little bit of a flare. And so we want to make sure that we are suppressing these edges as well of that signal. And so we want to make sure to grab that peak for sure at the notch. That's going to be endless. And then everything else, as we tighten this up, it affects those frequency ranges outside of that less and less and less. So for us, let's just say 10 hertz because we don't want to affect too much outside of it because we are down at the lower end, and lower frequencies are where most of our control operates. So most of the time when you see a mechanical resonance, you'll see it up at like 80, 90, 100 hertz, something like that, to where it's a little bit more pronounced. But this is just an example. And so what we would do from here is we would accept this band stop filter. Our accept button is grayed out. And at this point, when we click this filter effective, if we were online with this system, which obviously I'm not, I'm here down in offline mode. But if we were online, if this bar down here at the bottom was yellow, when we make that change and say accept, we can do that while it's running. Just make sure that your filter effective is unchecked. When you uncheck the filter, that makes it to where you can change things online. Once you check this filter, then it is going to actually put that filter into the current set point. Now, I don't have any real impact on what this would actually look like in a real system, but what you should see if this is a mechanical resonance, first of all, you will probably hear your system get quieter when you check that box. And I know it sounds insane, but if you have a real mechanical resonance that is vibrating and creating a vibration, it's going to be making a vibration in your ear that you can hear. It's going to have a hum. It's going to have a whir. When you check that box, it may very much just all of a sudden get quiet. I have an example of a system that was a chain drive system that the gears on it just sounded like they were grinding. And it was because they couldn't get really good tension on these chain drives. The moment I checked that box, all of a sudden the grinding went away. It didn't sound like it was fighting anything, because it wasn't, because it had completely eliminated the ability for the controller to excite that resonant frequency. It's pretty cool. So, and that's all that is. Now, here is what a signal looks like that doesn't have resonant frequencies. So let's go up. I have these other measurements up here. And on this metering roll here, torque actual value on the metering roll. Let's go in and do the same thing. Just real quick, frequency domain, we're going to select signal roll 80. We're going to accept it. It's going to chug, 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 chug. We have that measurement set selected. We're going to go to FFT. Now, it does actually have some up here, some resonant at 50 hertz. So let's undo this zoom completely. And so it's actually pretty evident here that there is a 50 hertz resonance. So it could be that signal, which, hold up, metering roll, time diagram. That looks pretty messy, but if you actually look at it, it looks like there probably is a 50 hertz. Oh, sorry. Yeah. So, right. So there is a peak up here because most of the stuff you can see is down super low, super low, and then it kind of comes back up. Now we may want to put in like maybe a 20 hertz band stop here on this signal, and it probably would help. But that 50 hertz is probably, I wouldn't know which one that would be. It's probably built into here. So if we like zoomed in, there's probably a 50 hertz waveform somewhere in here. But all that to say, let's see if I have another signal that doesn't have. Let's look at this, because I had one here earlier. All right, let's look at this. Let's look at a different measurement, because we don't have to measure the torque. We can go back in here, and let's look at one last thing. Frequency domain. Let's do signal, and let's do the metering roll R63, which is the actual speed on this one. And let's take a look at the FFT on it. There you go. See, there's no resonance in the speed of this, because you can see absolutely everything. It's all grouped down at the very bottom. You don't see any sort of like appreciable anything. That's what it's supposed to look like. And so hopefully when we put that current set point filter in, this system would not be making any sort of ringing. It wouldn't be making any sort of vibrations, because everything, look at this. The only signals are down 1.5 hertz. So that is a very tight, very good signal for that speed, this actual speed. So that is a well-tuned system. So, yeah. So, again, this was just a quick little live stream, because I haven't been able to do live streams very much as of recently. But what I do want y'all to know is that there are a lot of these tools, a lot of these things that are available, that as you come into this control world that Siemens has available for you, that most people don't know about, they don't use. And so hopefully this is one little thing that should be able to help you out a little bit if you have some sort of system that is giving you a little bit of trouble. Now, I will tell you, here is what this current set point cannot do. If you have an imbalance, say in a pulley, it cannot tune out that resonant frequency. Now, I will say, if you have an imbalance in a pulley, you will see a very strong frequency domain analysis. You will have a very strong pulse at whatever frequency your motor is turning at. And so when you speed up that spike, will move up that graph. It'll move up. And so the problem with this is if you have a vibration due to imbalance, this isn't going to help you. This is only able to tune out vibrations that are excited by the controller. Another thing on this is there is a video out there of a linear motor, and it has a kind of it's a spring. It's like a piece of metal with a weight up on the top of it, and it moves around and it kind of swashes back and forth because it's kind of a springy bit of thing. So that rock has some sort of spring constant based on the material properties and the weight of it and all of it. It's just a pendulum. Well, there's a video of somewhere out there of a Siemens linear motor that has this thing, and it's moving it back and forth. And so in order to actually, if it were to move, it would and vibrate and then kind of ring like a tuning fork, like boo. Well, there's two ways that you can keep it from ringing. You can move slowly and ramp up. You can ramp up the torque slowly and then slow down slowly like that. Or you can use this and it'll whoop, whoop, whoop. And it doesn't make sense. Like it seems like black magic, but I promise you, all they do is click the filter effective button, and all of a sudden, instead of doing this, it goes boop, pop, pop, because it's a spring force. It's the mechanical system is being excited by those few frequency components. Now, kind of talking about bearings and imbalance and all of those things, the way that you can see if it is a mechanical, if it's a resonant frequency or if it is a imbalance, is do the trace, do the FFT at different RPM. So do it at 100 RPM, do it at 200 RPM, do it at 3, 5, 1,000. And if that spike moves up, then you're kind of out of luck. It's an imbalance. I ran into another system that had some of these kind of periodic imbalance. It wasn't an imbalance. It was a torque ripple, and it was a periodic that showed up on this FFT. What this system was, though, it was gripping a piece of film, a very thin film, and it was kind of taking and stretching the film. Well, you had these grippers that would come in and grip the material as it's coming along. Well, you have this pop, 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 pop. That shows up in a FFT because every time one of those grippers would go over the mechanical roller, it would sit there and those grippers would be pop, 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 hitting over that roll. Well, that would show up as a ripple in your torque. Well, at every individual speed, that's going to be faster or slower. So if they're running slower, it's going to be a pop, 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 pop. Faster, pop, 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 pop. So I know y'all get that, but it's kind of an interesting thing because you'll be like, oh my goodness, here's this FFT. It's got this huge spike. And then you can't do anything with this. So I will say, if you do this and it works, you'll be a legend. You'll be the black magic magician. So here's a little tool, but yeah. So I will be putting this S120 test project and these traces available to you. I don't mind y'all seeing those. It's a random winder, and you can kind of play around with these trace files, doing different math functions on it. Maybe I'll try to come in and get a little bit more different values, different traces on some real systems. And if that's something that you might like, put that in the comment. But yeah, for now, I'm probably gonna start heading home. It's almost 6 here now. Maybe traffic's let up a little bit. Doubt it. But anyway, I'm glad that I've been able to actually do a little bit of a live stream. I'll try to get another one as soon as I can. It will be at least 2 weeks though, because I will be out of the country. I'm actually going over to Italy. So anyone in northern Italy that is seeing this before, say, February 20th of 2025, if y'all have some comment or in certain tourist areas or something that we could go through. We're going Milan, Verano, Cittadella, and I think we're going down to Rome. But things we should try, things we should see. Let us know if you're from Italy or you've been to Italy, or just, I don't know, maybe. And then maybe I can, I don't know, maybe I can get my wife to do a live stream from Italy, or let me do a live stream from Italy, maybe. But we are going up there to see some of our mechanical partners in agriculture, and at least hopefully be able to become mechanical closer partners. But a company called La Mechanica, they do some really cool pellet mills, really cool agricultural equipment, and they are up in that northern Italy area. So we're kind of mixing business with a vacation, but I can't go away just and do nothing. I mean, what would that be doing? Anyway, really appreciate you guys, and for all the people that have supported me through kind of the past couple of months, and just really all of it, all of 2024. 2024 seemed to fly by, but we had great growth on this channel. The members that have stuck through all of this, I thank you so much. If you have made it this far and you're not subscribed, why haven't you clicked the subscribe button? Because, I mean, yeah, why? You've listened to this voice for this long and you haven't been subscribed. Well, anyway, I'm gonna let y'all go. There's more where this came from, and I will be, doing more of these as always. If you got a suggestion for something that you want brought up or talked about on the stream or in a video, just drop in the comments. But anyway, take it easy, and y'all have a great weekend.